Here I want to talk a little bit more about similar triangles and ratios in similar triangles and some perhaps more advanced ideas that are sometimes not discussed in any detail in high school geometry texts. So here I have sort of a classic example of similar triangles. I have this right triangle here, A, B, C. Okay, it's actually the sides are 6, 8, and 10. That makes it a 3, 4, 5 triangle. And I'm going to drop the perpendicular down here from C down to the hypotenuse. Now, we've discussed this before, so I'm not going to go into detail on this, but this smaller triangle and this larger triangle are similar triangles. And it also turns out that both of these triangles are similar triangles with respect to the original triangle ABC. So we have three sets of similar triangles here. Now, and what I want to talk about is how, if we have two, for example, we have two similar triangles, and I'll talk about these two smaller ones, okay, this one and this one. We have two similar triangles, and let's say the ratio of the hypotenuse of the two similar triangles. So here's the hypotenuse of the smaller one, here's the hypotenuse of the larger one, is 6 over 8, or 3 over 4. And that's the same ratio we get by looking at the short leg of the small triangle as compared to the short leg of the larger triangle. That ratio of those two lengths is also 6 over 8, as is the ratio of the long leg of the shorter triangle to the long leg of the larger triangle. That's also 6 over 8. That's really what it means to have similar triangles. Now, but it's not just the sides of the similar triangles that have the same ratio. It's any one-dimensional feature that we might draw with respect to those two triangles. And in particular, I want to look at the circles that are inscribed. It will turn out that if we look at the radius of this smaller triangle and divide by the radius of the larger triangle, that is also 6 over 8, or 3 over 4. So, and because the circumference is just 2 pi times the radius, it turns out that the ratio of this circumference to this circumference is also 6 over 8, or 3 over 4. Okay, so I've taken the liberty of actually computing the radius of these two smaller triangles. So let me write down what those two radii are. Okay, this triangle right in here, this radius is 6 over 5. I've computed it. You might try computing it too. And this radius right here for this triangle is 8 over 5, which makes the ratio of the radii, this divided by this, is 6 over 5 divided by 8 over 5, or that's equal to 6 over 5 times 5 over 8. The 5's cancel, and that's equal to 6 over 8, just as I said it should be. Okay, 6 over 8, or 3 over 4. Okay, so we have then, anytime we have a one-dimensional feature, so for example, if we were going to draw this angle bisector here for that angle, and we were going to draw the angle bisector for the similar angle, which is this angle in the larger triangle over here, the ratio of the lengths of those two angle bisectors would also be 6 over 8. Okay? Now, let's talk about how areas compare, because while one-dimensional components go as 6 over 8, it turns out that two-dimensional components go as 6 over 8 squared, or 3/4 squared. So let's see how that goes. Suppose I were going to compute the area of this smaller triangle and the area of this larger triangle right in here. Well, again, I have taken the liberty of doing that, and I have that the area of this smaller triangle, okay, let me write that and say in green here, the area of this smaller triangle is it's 1/2 base times height, and I've taken the liberty of computing the base and the height so I could compute the areas here. And here, let me look at my piece of paper and see what I have for that. See, I have this dimension right here is 3.6. I've computed this. This is 3.6. That's the length of this line right here. Not 36, but 3.6. And the length of this line right here turns out to be 4.8. Okay, so that's the area of that line. Now, if this area is 3.6, that makes, I mean, this line is 3.6. This becomes 10 minus 3.6, or that would be 6.4. So this line is 6.4. Okay, so the area of this triangle is 1/2 times 3.6 times 4.8 times 3.6 times 4.8, and the area of this triangle is 1/2. Let's call this, so we'll call that area 1. The area of the larger triangle, area 2, is 1/2 times 4.8 times 6.4. So I take the ratio of the two areas. So I take area 1 divided by area 2. This would be area 2. Area 2. Okay, so that's 1/2 times 3.6 times 4.8 divided by 1/2 times 4.8 times 6.4. Okay, so doing this, the 1/2s in the numerator and denominator cancels, and the 4.8s in the numerator and denominator cancels, giving me 3.6 over 6.4. Over 6.4. That's the same thing. That ratio is the same thing as 36 divided by 64. And that ratio is the same thing as 6 squared divided by 8 squared, or 6/8 squared. So I say that the areas of any two similar features are going to go as the square of our similarity ratio. So if the similarity ratio between the sides is 6 divided by 8, the areas of the features are also going to go by 6 over 8, but squared. So the areas go as that similarity ratio squared is. In a similar fashion, we can compute the area of this circle and the area of this circle. Now, I said that the area of the, I've computed the radius of this smaller circle, okay? Now the radius of this smaller circle, I said, is 6 over 5. And the radius of the larger circle is 8 over 5. Notice, by the way, that the ratio of the two radii is 6 over 8. Okay, again. Now we know that the circumference is 2 pi times the radius. So the circumference of the smaller circle is 2 pi times 6 over 5ths, 6 fifths. And the circumference of the larger circle is 2 pi times 8 fifths. So it means the ratio of the circumferences are, that cancels, 6 fifths divided by 8 fifths, which is still 6 over 8. So the circumferences, being one-dimensional features, have the same radius of 6 over 8. And the areas are pi r squared, so we have the area of the smaller circle is pi times 6 fifths squared, and the area of the larger circle is pi times 8 fifths squared. So it means that the ratio of the areas, again, we cancel out similar terms in the numerator and denominator, still goes as 6 over 8 quantity squared. So, again, one-dimensional features like circumference and radius are going to have the 6 over 8 ratio. Areas, like the area of the two circles, will have the ratio of 6 over 8 quantity squared, which, as you know, is the same thing as 3 over 4 quantity squared. So this is what I wanted to tell you, this little added thing about similar triangles and similar shapes in general have this property. So next time.